Good day and welcome to running the Statistical Gauntlet in SAS. This is a companion to running the Statistical Gauntlet in R. I'm Dr. Mark Williamson for the Biostatistics Core at DaCCoTA for the University of North Dakota. So a bit of an introduction and background of why I'm doing this presentation. In Introduction to Statistics, it's common for a single or a couple examples to display each model or technique. This is good when you're first learning the ropes, but it doesn't really help you in adapting the example to your own particular work. And it doesn't really help you train your eye or train your intellect into understanding patterns that these tests or these software churn out. So this presentation is aimed at remedying that by exhaustive back-to-back examples. Now, this is aimed at more intermediate learners that I'm not going to go over any of the sort of basic underpinnings of a lot of these tests or statistics. I'll have to assume that you already have that coming in. And so get ready for what I'm calling a gauntlet. I hope it'll really help you and serve you well. I'm going to try, there's a lot of material to cover. We're going to try to get it under 30 minutes. If not, well, then you can just down a pot of coffee or a case of energy drinks and watch this video at 1.5 speed. That'll get you there. So, before we move any farther, just ask you to take this pretest. Stop and take it at the link here. It's also available in the description below. So please take the pretest, and then when you're done, please take a post-test, and then do a very short survey about how we did. Okay, let's jump into our overview. We'll be using SAS Studio. So you can, it's a free version of SAS, so that's why I like to use it. You can get it yourself at this link here. And then the code that I'm actually using today, I'm not really showing any of the code, but any of the code is available at this link here. So you could follow along later if you'd like. So the topics we'll be covering here come in three broad groups: t-test, ANOVA, and regression. We're looking at three kind of basic tests in each of them. One sample, two sample, and paired t-test, one way, two way, block nested ANOVA, then simple multiple logistic regression. So the procedure for each test, there are going to be six examples per topic. Now I'm going to be ignoring most assumptions, explore data, model building, etc., and condensing a lot of the SAS output to just sort of the core things we need to look at. This is all for brevity. Obviously, if you're doing this for real, for your own studies, obviously you need to do a lot more here. This is sort of a quick gauntlet. Now, I'll be showing the test statistics in purple, p-value, and then in yellow, and then when appropriate, a model fit, if that is relevant, in blue. And so each example here will have a research question in the form of a sentence to sort of get you thinking in plain language about these statistical questions, the results from SAS, and a lot of times I'll round some of the numbers for brevity. Then there'll be a written answer to the research question, so again, plain language answering it, and then figures or table when appropriate. Now, you typically don't show no results, no like non-significant results, though I will for clarity, and I'll have them outlined in red. Again, only significant results in papers are usually presented. So get ready to run the gauntlet. Let's get started. All right, let's get this gauntlet party started. We'll start with the one sample t-test. It tests if a variable's mean is different from a set value. So for each of these, we have to have a set value, which we'll give. So for example, one, we have average birth weight of infants and whether it's different from this value of 3,200. We get some condensed results from SAS. Our t-value is our test statistic, and then the p-value is whether that's significant or not, and this is below 0.05. So yes, birth weight is significantly greater than 3,200. From a mean, we see that, yeah, it's about 3,400. We asked the same question about black infants, but now we could say that whether they're less. And again, that's significant. It was significantly less than 3,200 because it was, in fact, 3,162, and that was significant. We could compare the two by setting our set value of the white infants against black infants. And again, this is significant. And now we're asking a little bit different question than greater or less than. This is a two-tailed, so it's different. So it looks in both directions. We find that it is significant, but to tell which direction, we have to look at the mean. So our value is 3.4. This is 3-1, so black infants were significantly less than white infants. All right, let's switch to some baseball. Look at the average number of at-bats for baseball players. I think this is for season 1986. Whether it's different than 400, we find that no, it's not significantly different. While it is slightly lower than 400, it wasn't significant. Again, we could ask the same thing with log salary. If it's different from 6, we find that no, it's not significantly different. Finally, let's look at, is the average number of home runs greater than for a single player, say Barry Bonds here? And what we find here is kind of interesting. We have a large t-value, but the p-value is not significant. That's because we're only looking in one direction. We're asking if it's greater, and this is clearly less than 16. So no, it's not really different than 16. Let's gallop along to 2-sample t-tests. Very similar, but now we're testing the mean of 2 different groups is different, rather than one mean and then a set value. So we can go back to that infant birth weight. We can ask if there's a difference between boys compared to girls, or if boys are greater compared to girls. So now here we're going to have a little more data because we want to test certain assumptions about variance, and then given the outcome of the test, we'll use one outcome over the other. So first we have these equality of variances. Now, because this is significant, we're going to use this Satterthwaite method, which is for unequal variances. So if this test for equality of variance is significant, it means they're unequal, so we have to use this test. It doesn't really make too much of a difference here, but it might. And sees that this is significant. And yeah, it looks like birth weight was significantly greater for boys. So it's coded boy as 1, and we see it's about 3,400, where girls are 3,300. And here's a graph here. It's a little hard to see, but the boys are here. So we could look at another category for birth weight, smoking versus non-smoking mothers. Again, we do this. Again, this was significant, so we use Satterthwaite. And yes, birth weight was significantly lower for smoking mothers. So you see here now this is lower. And we can see here, yep, smoking mothers had higher, or non-smoking mothers coded at 0 had higher birth weights. And we can look at between married and non-married mothers, same sort of thing here. We're going to get a significant value, so birth weight was significantly greater for married mothers. Okay, let's jump back to baseball here. Is the average number of hits for baseball difference across league? So now we have our equality of variance is not significant, so we can just use the equal variance section here, the pooled, to get a just insignificant value. Close, but it's not significant, so it wasn't different across league. And this is, again, these aren't significant results, that's why I have them in red. We can see here that the kind of confidence intervals overlap quite a bit. We just ask the same question, but for number of runs rather than hits. Again, not significant, so we use the pooled. And now this is significant. The number of runs was significantly greater for the American, 55, versus the National League. And we see here that these are spread out more. Again, we could look at outs for across division now, East and West. Again, we'll use pooled, and no, there was no difference. This is practically identical. Okay, let's wrap up our t-test by getting our paired t-test. And this takes a specific kind of data. Test if the means of 2 different pair groups are different. So these aren't just like male and female, yes, no. These groups have some sort of pairing, some sort of non-independence. So let's look at some pricing data. Is the average unit price different across time for product 1 and 10? So they're 2 different products, but same time period. That's how they're paired. What we get out here, so now this paired test is really is asking, is the difference, so this is the mean difference, is it different from 0? And so we find here that, yeah, that was significant. Unit price was significantly higher for product 10. Well, how do we know that? I like to use these spaghetti plots. So this is product 10, this is product 1, and it's an upwards trajectory here. So it's on average more expensive for price 10. We can do the same thing for other products, product 1 and 14. Again, that's significant. Not quite as strongly, but it is significant there. And then we could do, say, product 16 and 17. Again, it's significant. But in this case, product 16 over here was significantly higher than product 17. Let's change tact here and look at perch and two different lengths between measurement 1 and 2. So this is two different measurements on the same individual. That's how they're paired. So the mean is negative 2.16. So this was significant, and it turns out that measurement 2 was significantly higher than measurement 1. And you can see here that like every single line, every single measurement in 2 is greater than 1, because it turns out measurement 2 was a slightly longer version of measurement 1. So this probably wasn't the best data because it was sort of obvious what's going to happen, but this is just, you know, to find the right kind of data. This is just an example I had here. So probably won't do this in real life, but you can run tests on anything. Okay, let's look at blood pressure difference before after a stimulus. So we find that this isn't significant. So we see here that while some may have gone up or down, this sort of line here is pretty much flat here. And we could ask another question, sort of about more health related, like 5 was. Is the average area under the serum concentration curve different between a test and a reference drug? So again, these are in the same individual. So this was, again, not significant between drugs. So there's the test and the treatment. And again, the line is a little steeper, but it's still not, it kind of washes out. It's not, there's not a significant relationship. Okay, that covers t-tests. Let's look at the more or less the extension of the t-test, ANOVA, which tests if a variable's mean is different between a category with 3 or more groups. So a t-test would be 2 groups, ANOVA 3 or more. So the one way is the most basic one. Let's take a look at some examples here. So let's look at the classic iris dataset. Is the average sepal length different across species of iris? So now we're going to have a little more data here. The main thing is that still F value and a P value. And if it's significant, we'll have to follow that up by looking at which groups are different. So yeah, we know that they're significantly different because this was significant. So a lot of times we can plot these. It looks like Setosa is the smallest, Virginica is the tallest, and then this one's in between, but are they all significant? We usually have these Tukey tests. So this output in SAS shows the ones that are covered by the same bar are not significant, but since they all have their own bar, they're all significantly different from each other. So all significantly different. All right, let's speed this up here. We can do the same kind of question, but now with pedal width instead of sepal length. Again, that's significant. It looks even more so. Again, they're all significantly different from each other. All right, let's keep jumping. Let's turn to cars. Is average car MPG different across origin of car? So this was significant. It was different across origin. We can see here we have Asia, Europe, and USA as origins, but now here we have a little bit more of a table. So it'll take a little more to decipher. Each of those shows a comparison if they're significant. They have it here, and really what it's saying here is Asia is significantly different from these two, but these two are not significantly different from each other. Now we could look at suggested retail price against car type. Again, this is significant. It was significantly different across type. We have more types here, so these are more than 3 groups. There's 5, and as ANOVA groups increase, the sort of comparisons you need to make to distinguish which ones are different from each other increases as well. But as complicated as this is actually fairly simple. It turns out that all the ones that are significant have sports in them, which means that, and then none of them else have them, which means sport cars were significantly, looks like, higher compared to all the other ones which weren't different from each other. So not surprising, sports cars were more expensive than other types of cars. That's why you buy a sports car. Anyways, then we could ask, is average width different across different fish species? I showed just 3 out of a data set, and this was not significant because the p-value was greater than 0.05. I'm plotting it. You can see here that, yeah, it looks like they're pretty much the same. There's some variation. What if we looked at 6 species, kind of broadened it out? And now this is significant. It was different across species. You can see that there's much more of, this is for length, not width. And so again, we'll have to look at this big table. There are other ways to do this in SAS, but this is kind of the simplest way to output it. It just takes more interpretation. I'm not going to go into all of it, but looks like, for example, Pike is pretty much different from all of them, and then there's other comparisons that are going to be different. Like this looks like it's going to be different from this. You would need to tease all this out and usually use letters or numbers above them if you're plotting this for a presentation or paper. But there we go here. All right, let's charge forward to two-way ANOVA. It tests if a variable's mean is different between two categories with multiple groups each. So instead of one category like one-way ANOVA, we have multiple categories, two categories. So is average height different across age? That's one category, and sex another category. We could also look at the interaction. So the results we have here, it looks like we have to look now at multiple f values and p values, and we see that initially these are both sex and age are significant. This isn't matching this. We'll see in a second here. So this is the interaction. It wasn't significant, so they don't overlap. But then if we look at these, follow up with two-key test, it turns out that, we see here that sex here was just barely significant, but if we take in correction with two keys, this is no longer significant. That's why I didn't include it in our text here, but age still was. So now let's look at these children, but let's look at weight. Again, we have here two that are significant, but now this time these both and the two-key test were significant. So we can see that looks like here males were heavier, of course, and then older kids were heavier as well. Not surprising, what we'd expect. So let's shift over to baseball. I hit this out of the park here. We're looking at league or division. And what we find here is that no, none of these were different for the average number of hits. And again, this is a nice interaction plot to kind of look at all these at once. Nothing really going on here. What about log salary across league or division? Well, it looks like division was significant. So interaction plot, not much here, but log salary and division, it looks like the East had a little bit more than the West for average log salary, and these were significantly different by the two keys post hoc test. Okay, let's turn to cars, horsepower, and origin or drivetrain. We find here that both origin and drivetrain were significant, but not their interaction, so we don't really need to use this, but we'll plot these individually. And again, we need to do these post hoc tests and kind of look at differences. And it turns out all of these were significant for everything, so it looks like horsepower is significantly different across all three origins, European, Asian, and US, as well as drivetrains. Okay, let's keep going here. Let's look at birth weight again and maternal education level or smoking status. Looks like all of these were, even the interaction. And that's why I went through the effort to plot a more complete kind of bar graph showing that across the board, smoking mothers had lower infant birth weights than non-smoking, and it looks like also education level sort of has an effect too. Lower, like education levels 2 seems to have the highest compared to the other ones, but I think these are all different. All right, we've made it to what I would say the thorniest or hardest to sort of understand, kind of gnarly conceptualization is blocked and nested ANOVA. Tests if a variable's mean is different across categories like a normal ANOVA, but it counts for more complicated designs like blocking or nesting. So let's jump into an example here. This looks at average response across school and instructor, but then instructor is actually nested in school. That is like there's instructor 1, 2, 3, it's in school 1, and then another instructor 1, 2, 3, school 2, etc. And so we have this, and we have school, and then this instructor school, and we find that they're both significant. Response was really different for both school and instructor, and so I have both of these here. What we see here is that Atlanta is significantly different from Chicago and San Francisco, where it's a little bit more complicated with looking at both instructor and school, but you can't really just look at instructor alone because it's kind of nested. We see the ones with the highest response were Atlanta instructor 1, and then so forth. And we see here that in this output, we get sort of the numbers like A, B, and C's to be able to fill out this graph if we want to later on. Okay, let's look at another example. Average log revenue of airlines across flight type, so flight type, and that is nested in flight source. Now this time we included it flight type, but we didn't care about it. We just included flight source in the outcome, and we find that that wasn't significant. And again, this is some output. We see that these kind of are pretty spread out across source. And then this is we actually had this as what we call a random effect type nested in source. We saw that one of the reasons to kind of show this is the covariance for our type that we included in here is large compared to the residual, showing that it made sense to include it in the model, even though it wasn't ultimately significant. Okay, let's keep moving on. We have one more nested effect. So calcium levels across turnip plants where samples are nested in leaves and plants. So we have multiple levels of nesting. We only care about plants, so that's what's here and significant. They were significantly different across plants, but then these were we had those nesting levels as covariance as random effects, and looks like, while leaf was pretty big, we probably didn't need to have sample, but heck, we did it anyways. And we look and we see here, it looks like plant 4 and plant 1 were together, so those were the A's, and then plants 3 and 2 were a group, those were the B's, those were lower. Okay, let's switch over to more of the blocking. Is average cell damage different across drug dose when controlling for rat? So now rat, we're just including the model to control for it, but we don't actually care about it. And what we find here with dose, that was significant. And again, we have this sort of covariance showing that, well, not as much as the residual, but that's good to know here. And yeah, it definitely look like this is on its own. 200 is on its own, and these are on its own here. So different groups here, significantly different from each other. Okay, let's keep going with blocking. Again, so we're going to look against sex in children for height, but we're going to control for age. Like instead of looking at both of them at the same time like we did for 2A and over, we're just going to control for age because we know age is different, and that was not significantly different. And yeah, age was definitely an important thing to control for, how big of it was compared to residual. And we see here that males are bigger, but not significantly. And against these output, these were both A's. Okay, last one here, different across sex when controlling for age for weight, so very similar. But now this time it was significant, and again, age was important to add as a blocking effect. And yeah, males were a little bit heavier. Okay, let's switch over to simple linear regression. We had categories with ANOVA and t-test. Now we just have numerical ones. So a relationship between a numerical response and numerical predictor. So simple linear regression. Can the log number of votes be predicted by population in U.S. counties? So we're going to have an intercept, but we're only going to really look at this variable here. Intercept is important for the line of best fit, but not important for the outcomes here. Okay, yeah, there is a significant negative relationship because this is negative. As population increased this way, log voting rate decreased. And you see there's a lot of data. It's a little messy. We'd probably clean this up or do model fitting if we had more time, but we don't because we're gauntleting. Come on. Log weight, log length in fish. Well, again, we see that that's significant as log length increased, log weight increased in fish. Not surprising at all here. What about weight and width in fish? Yes, again, very strong relationship between the two. As one increased, so does the other. That's a positive relationship as opposed to the negative in the example 1. All right, let's jump a little bit here to, again, baseball. Number of home runs predicted by the number of hits for a baseball player. That was significant. As the number of hits increased, so did the number of home runs. What about number of years in the major leagues and the number of runs? Oh, nope, that was not significant. We can see here that, yeah, it's pretty much a flat line. The number of years did not predict number of runs at all. What about log salary, and can that be predicted by number of runs? Yes, that was significant. As the number of runs, the log salary increased, which kind of makes sense. Hopefully the people who are doing better and getting more runs are paid more. So now let's jump to multiple linear regression, the extensive simple linear regression. Now there's a numerical response variable. Again, that's y, but now there can be multiple predictor variables, so multiple x's. So we're no longer going to be able to usually plot these, because those scatter plots are in 2 dimensions. We'll jump up here and usually just talk about numbers and stuff. So can we predict log number of votes by population, education, housing? So with multiple regression, often you can't add everything, so sometimes you do model selection. And so I'll show that here. It turns out, yeah, if we add all of these, it significantly adds to the model. Here, again, we were looking at multiple t-values, and we find that they're all significant. So yeah, there's significant relation between population, education, houses. It looks like that it was a negative relationship with population, but then positive for education and housing. We could ask the same kind of question, but then look at all interactions as well. And again, we're going to do stepwise selection, and it's going to stop here telling us these things we're going to add, and then we're going to have even more. You can see as multiple regression, it can get bigger and bigger models. And we find that pretty much everything was significant. Well, everything here was significant. There we go. Okay. All right, moving on here. Let's keep it up, keep it going. All right. What about in fish? Log weight predicted by all these variables, length, bunch of lengths and other things. So we did the stepwise selection, and it gives us this. But now, since these are all pretty, you don't want to add things that are correlated with each other too highly. 0.08, sort of the cutoff and higher. So what we want to look at here is some correlation coefficients, and what we find here is that, unsurprisingly, width, height, and length are all highly correlated to each other. So you just want to take the one of them and include in your model, the one that's usually the most correlated with our y variable, which is weight we care about. It turns out width is the most correlated to weight, so we're going to drop these and just have width, and we get that. It ends up being significant, and we can plot it. Unsurprisingly, weight can be predicted by width. Yes, significant positive relationship. So again, let's do this with baseball players. Again, so we need to do this correlation, and it turns out that number of hits and runs are highly correlated, but the number of hits is slightly strongly correlated to log salary, so we'll include that in a model. So our final model with hits and home looks like they're both significant. As log salary increases, the number of hits and home run increased. All right, keep it up here. Let's look at log salary with even more variables and a lot going on here. But it looks like there's no correlations at 1.08, so we'll keep that all in our model. And what we find here is log salary increased with hits and years in the major leagues. So there's only 2 that were significant. Okay, finally, let's look at same sort of thing with log salary, but even more variables. We'll do some model selection, stop here, do some of this Pearson correlation coefficients. It turns out number of hits and number of at-bat were highly correlated, so we'll just keep number of hits. And again, we find that there were some significant number of hits, walks, that's NBB, and years in the major league, that was significant. Okay, finally, we're here at logistic regression, just about the 30-minute mark, so let's speed it up here. So this tests the relationship between a binary response variable and one or more predictor variables. So we're used to the other regressions, your y variable being continuous, like weight, height, but now these are binary, 1 or 0. So let's look. Can fuel status, so 1, ethanol, or non-ethanol, 0, be predicted by nitrous oxide emission, a continuous x variable? Find that that was significant. And again, I'm going to do some model selection. It's nice to show that this Pearson chi-squared over degrees of freedom should be about 1, and for logistic regression, it's usually exactly 1 because that's exactly what it is, binary data. So that's a good fit. And yeah, there was a significant negative relationship. As nitrous oxide increase, the probability of ethanol decrease. So these plots with logistic regression, it's probability. So the probability of it being ethanol, if 100% is over here, 0% down here. So as nitrous oxide goes up, the probability of you having a value of 1, ethanol goes down. Similarly, we can look at equivalence ratio, and that was not significant at all, though it did have a pretty good fit. You can see it's pretty much a flat line. There was no relationship. What about junk mail status? So 1 is the junk mail. I think this should be a 0. Predicted by the frequency of exclamation marks in the mail text. And that was highly significant, though Looks like this isn't a very good fit, but there was significant positive relationship. As the frequency of exclamations increased, probably would be junk mail increased. So, but it didn't have a very good fit. I'm not sure why. You actually, if you were doing this for real, you'd have to really dig into building a more sophisticated model. Okay, continuing our junk mail theme. Again, this should be a 0. Let's look at more than just one X variable. We can look at a bunch of frequency of words and symbols. And what we find here is, yeah, this wasn't a good fit, but leaving that aside, report and address were not significant, but all the other ones, as their frequency increase, the likelihood of it being junk mail increases as well. And this sort of the words and symbols you'd expect in junk mail. So now let's shift a little bit. Let's look at death status. So 1 is dead, 2 is not dead. Be predicted by risk category. Now instead of a numerical variable, this is actually a categorical variable. You can do that with logistic regression, though the output will be a little bit different. We'll explain a little bit differently. So we found that that was significant. There was at least one group that was different from each other. And then that was a good fit. And then what we get here is our estimates. So essentially we have a reference. So this is our this kind of leukemia, ALL. And then we're comparing, so that's why it's set to 0 while comparing these other ones. So it looks like low risk is lower and AML is higher, but looks like these actually, while the model itself was significant, it looks like the individual comparisons was not. In fact, what we typically do is look at odds ratios, which compares the groups to a reference. So the high risk group compared to just the normal leukemia, and the low risk compared to leukemia. This estimate, this is the odds ratio. If it's above 1, it means it's more likely for this group than the reference. If it's less than 1, it's less likely. So this says that it's almost twice as likely for this AML high-risk group to die, so having a status of 1, compared to the ALL, where the low risk was almost half. But we know it's not significant because confidence intervals, if they overlap 1, it means they're not significantly different, and these do. This goes from 0.6 to 4, and this goes from 0.2 to 1. So while they were different, it wasn't significant in the sort of the post hoc tests. Now let's look at car type, sedan or otherwise, predicted by these different categories. Yeah, we get more than one category for logistic regression. No sweat. What we find here is that origin and drivetrain were significant, and then what the interpretation of this is, now this was not significant because these overlapped 1, but these were all significant. So it looks like Europe versus USA. Europe's had a European car was more likely to, almost twice as likely to be a sedan than otherwise. And then for drivetrain, looks like both all-wheel drive and rear-wheel drive versus front-wheel drive were less likely, because these were less than 1, less likely to be a sedan. Okay, wow, we've made it through that gauntlet. Give yourself a pat on the back, though maybe take off your gauntlet first so you don't hurt yourself. I'd like to make some quick acknowledgements. So if you want the reference for SAS-code, again, that link is here. The references for the title image I use is from Wikipedia, and then there's selected examples that I use from other sites. Some of the data data sets I got from there, I want to acknowledge them here. All other data sets were from in SAS help on SAS Studio. So again, I'm part of DaCCoTA. We're funded under the NIH, so please reference us if you find this useful for your presentations and publications. Thank you, and hope you enjoyed this gauntlet.